Bismillah ar-Rahman ar-Rahim. Today, inshallah, I will continue with the eigenvalue problem. We are going to find how to get integer powers of diagonalizable matrices using an easy way to compute, for example, something like a power 100. If the matrix is diagonalizable, you will find an easy way to find something like this. And then to generalize this to find functions of diagonalizable matrices. Actually, any function that can be written in power series in matrices, you can find it easily using diagonalizable matrices. And as you know, not all matrices are diagonalizable, so there are other ways to find these guys, integer powers of matrices and function of matrices. We're going to study one method called based on Cayley and Hamilton theorem to find integer powers of matrices, whatever they are diagonalizable or not, and in general function of matrices. So first, as you know, this chapter 5, is basically relies on the eigenvalue problem, which is the problem of solving this equation. When you have a square matrix A, you are going to find a non-zero vector x such that the transformation Ax leads to a scaling of the vector x. And this scalar is called the eigenvalue, and the vector is called the eigenvector. And if you remember the steps to find these guys, x and lambda, the first step is to get lambda from which is called the characteristic equation. You find the characteristic equation, solve this equation to get lambdas, and then for each lambda, get back to the original equation to find the eigenvector, which you can write it in one side this way and solve this homogeneous system. And this system must have infinite number of solutions. There must be free variables in the solution. And then we moved on to the diagonalization, and we said that the matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. And then you take this linearly independent eigenvector and put them in a matrix P, and you will get this equation. AP equal P times diagonal matrix containing the eigenvalues, such that P is n by n also like A, and the invertible matrix, such that you can multiply by the inverse of P both sides to do what is called the diagonalization of the matrix A. So multiply A by P and P inverse from right and left to get a diagonal matrix containing the eigenvalue, and this process is called diagonalization of the matrix A. Then to do the diagonalization, you must have matrix P containing the eigenvectors and linearly independent eigenvectors to be invertible matrix. Okay? Another way to write this equation is to get A subject D, so you can multiply by the inverse of P to get these four. So we have actually three forms for the diagonalization equation. The first one, and this guy, and this guy. And here we emphasize that P is a square matrix containing n linearly independent eigenvectors and D containing the corresponding eigenvalues. Let's review this through an example quickly. For this matrix, you first solve to get the eigenvalues and eigenvectors as we did before. So you write the characteristic equation and solve for lambdas. So you'll have here lambda equal 1 and lambda equal 5. And then solve to get the eigenpairs, which is the eigenvalue and eigenspace. So for eigenvalue equal 1, we have this eigenspace. And for eigenvalue 5, you have this eigenspace. Then you have actually many solutions for the diagonalization. You have many p's. One of the p's could be to take these guys as columns in the matrix P. And as you see, if you put these guys into the matrix P, you will get a square matrix that is invertible, so you can do this diagonalization. Okay? Is this matrix invertible? Because its determinant is 4, not equal to 0. And the diagonal matrix here, you write the corresponding eigenvalues to each column here in P in the same order. So for example, this guy has an eigenvalue of 1. So the first element in the diagonal matrix would be 1. And for this vector, the same eigenvalue 1. So we'll get 1 in the second entry on the diagonal. And for this vector, 5. So this would be your diagonal matrix. You can do this check, multiply inverse of P, inverse of this guy by A by P, and then you must get this diagonal matrix according to the theorem. So this is called the diagonalization of the matrix A. And we said that you can check if your matrix is diagonalizable or not from the multiplicity of the eigenvalues and the dimension of the eigenspaces. I call it a recap of the previous lecture, okay? So here we have the multiplicity is the number of repetition of the eigenvalues as a root in the characteristic equation. So we have for lambda equal 1, multiplicity equal 2, and for lambda equal 5, multiplicity equal 1. And the dimension of the eigenspace for lambda equal 1, the dimension of this space is 2, which is the count of the number of bases in the space. And the dimension of this eigenspace is 1. And we said that you know that the matrix is diagonalizable or not if the multiplicity equal to the dimension of the eigenspace for each eigenvalue. Okay? So we said that you can know that the matrix is diagonalizable if you have several cases. If you solve the characteristic equation and you find distinct eigenvalues different from each other, so you can know that the matrix will be diagonalizable. So this you can know it from solving the characteristic equation. If you have distinct eigenvalues, it would be directly diagonalizable and complete and find the eigenspaces and form your P. In general, if you have a repetition of the eigenvalues, you have to check that each eigenvalue that has multiplicity greater than 1 has the same dimension of the eigenspace. And if you see that your matrix is real, not complex, real matrix and symmetric, then it would be directly diagonalized. These are the main guides to know that the matrix is diagonalized. Let's take this form of the diagonalization. The other form. What is the other form to write? A subject D. What is A? Can get A from this equation by multiplying this guy by inverse of P from right. So we'll get A equal P D inverse of P. Let's try to find the powers of A using this diagonalization equation. Suppose that I want to find A square. So I write P D inverse of P, P D inverse of P. Let's simplify it. We'll have here identity. So we'll actually get here d square p d square inverse of p. We do this, the same to get a power 3. It would be p times a times a square. I'm going to use this a square and a. So we'll end up by p d power 3 inverse of p. So you can generalize to have a power k. It would be simply p d power k inverse of p. So if I want, for example, to find a power 100, so this would be p d power 100 inverse of p. So this is simpler than this guy, right? If you have a diagonal matrix and if you want to raise it to the power 100, for example, if you have 2, 3, and we want to raise it power 100, 2 power 100, be simply like this. So this is very easy to compute. So actually the effort here is to find p and the inverse of p, and then multiply with 3 matrices to get a power 100. Okay. What about the inverse of a? Can we do something like this to get the inverse of a? Using the diagonalization equation, p d inverse of p, take the inverse, so distribute the inverse in reversed order. So we'll get p d inverse p inverse. If you look at these guys, they take the same shape. P inverse, and in between d, p inverse in between d power 100, p inverse, and in between d power -1. Okay? So whatever the function here applied to a, you replace it here with the function applied to the diagonal matrix containing lambdas. Is it simple to find the inverse of something like this? The diagonal? What is the inverse of this guy? 1 over 2, 0, 0, 1 over 3. Right? Okay. So for this example, if I ask you to find a power 100, don't multiply a by itself 100 times, okay? I'm going to use the diagonalization. So the effort would be in finding p and the inverse of p. Is this matrix diagonalizable? Can you know before starting the eigenvalue problem? It is real symmetric, so it's going to be diagonalizable. Okay? If you solve, you can get the eigenvectors and put them in a matrix P, and these are the corresponding eigenvalues, 3, 3, and -6. So a power 100 equal P times diagonal power 100 times the inverse. This guy is the inverse of the matrix P. So multiply these guys to get a power 100. Simple? Okay. Okay. So as you see here, whatever the function on A, you can find this function on the diagonal to get the expression. So let's define what is called the matrix exponential. Do you remember the exponential function, e power x? Do you know its Maclaurin series? 1 plus Okay. طيب. You know that the derivative of e power x is e power x, right? طيب let's do something like this for the matrices. I'm going to define E power matrix, E power A, using the expansion. So replace X by A, okay? So we'll have here A, A square over 2 factorial and so on. What to write here? Identity بقى مش كده؟ طيب this guy you can write it in compact form as Guda said, summation x power k over k factorial k from 0 to infinity. Let's write this also in compact form, summation form. So I write it as a power k over k factorial k from 0 to infinity, such that a power 0 is defined to be the identity. Okay? How to find this guy? Let's use the diagonalization to find this guy. I want to find e power a, but I don't want to sum up to infinity. So I want a closed form for the exponential. So let's replace a by its diagonalization form. So e power a equals summation a power k. Let's write it as p d power k inverse of p over k factorial. Do you have anything that is not function in k inside the summation? You can take it outside. I can take p and inverse of p, but preserve the position of each guy. And let's expand this guy. What is the first matrix here? This is summation of matrices, and all are diagonal matrices. The first one, k equals 0, will get d power 0, which is identity. So you'll have the identity matrix. What is the second guy? D power 1, which is the diagonal containing the eigenvalues. So you'll have the eigenvalues here over 1 factorial. The next matrix would be 1 over 2 factorial d square, right? So you'll have lambda square and so on. And here you have inverse of p. So these guys are diagonal matrices, right? So let's try to find the first entry. Don't forget the factorial. So the first entry would be 1 plus lambda 1 plus lambda 1 square over 2 factorial and so on. So it would be e power lambda. And the same for the other lambdas. So we'll end up by e power a equal, again, p inverse, and in between diagonal matrix containing the exponential of lambdas. So whatever the function here on the matrix A, you simply replace it by a diagonal matrix containing this function on the eigenvalues. Okay?
انا معنى كده ان انا اقدر احسب مثلا سكوير روت اوف ماتريكس، ولو ضربت الماتريكس دي في نفسها هيديني الماتريكس الاصليه.
دي كانت البروبلم بتاعت الفاينل اكزام لاست يير اللي انت بتقولها. طيب, let's try an example. Find e power a for this matrix. Simple 2 by 2 matrix. I want to find e power a. So e power a is simply p diagonal e power lambda inverse of p. So I have to solve the eigenvalue problem, verify that the matrix is diagonalizable, and then apply this rule. Okay? Can you know that this matrix is diagonalizable before you solve, or you have to solve diagonalizable? How do you know?
eigenvalue بتاعتها هيبقى 0 2
فعلا? I have to write the characteristic equation and find the lambdas. If the lambdas are two distinct eigenvalues, then the matrix is diagonalizable. Okay? ما يطلعوا كام بقى؟ يطلعوا 2 and negative 4. Then you know that the matrix is diagonalizable. Then complete and find the eigenvectors and write your P. These are actually the eigenpairs. 2 with the eigenspace, negative 4 and its eigenspace. So one of the P's would be 1, 2 and 1, negative 4. This is your matrix P. And to write the exponential of A, you multiply this matrix P by diagonal containing e power lambda by the inverse of P. So this is P containing 1, 2 and 1, negative 4. And here you are going to write its inverse. And in between, diagonal containing the same function applied on the eigenvalues. In the same order, you write the eigenvector. So this eigenvector corresponds to the first eigenvalue 2. So write first e power 2, then e power negative 4. Multiply these guys, you will get a matrix called the exponential of a matrix. Actually, I'm going to use the exponential of a matrix next lecture, inshallah, to solve the system of differential equation. Okay? Let's first extend what I did here. Instead of finding e power a, I want to find e power at. I'm going to add t here, where t is scalar, which represent usually the time of your differential equation. So what is going to be changed in what I did? You are going to replace here t and so on until you end up with e power at equal, what do you expect? The same function, replace a by t, by lambda, okay? So it would be something like this. So in general, e power at, p, p inverse in between, the same function applied on each lambda on the diagonal. We write it this way, p diagonal e power lambda t inverse of p. Let's see some properties for e power at. And this is actually what I'm going to use in the differential equations. E power at. What about e power a times 0? If you replace t by 0, what do we get?
e power الايجنفاليوز اللي e power 0 فهتدي
By e power 0 matrix, which is identity.
هي ال t sub e lambda t دي هتطلع الايدنتي.
دي هتطلع الايدنتي. انا هحط t equals 0. ف t equals 0 يبقى دي e power 0 على الدايجونال اللي هي 1s. فتبقى p times p inverse تبقى الايدنتي. Or from the expansion اللي هو المكلورين expansion حط t equals 0 فالريميننج هيبقى ماتريكس واحدة الفيرست ماتريكس اللي هي الايدنتي. But this guy is going to be identity. Okay. IN. What about e power a times t plus s? T and s are scalars.
d sub e lambda t plus s times p
Replace here t by t plus s. تطلع كده. ماشي. هي سهلة في الدايجوناليزيشن. في الدايجوناليزيشن يبقى P diagonal e power lambda t plus s inverse of P و e power at times e power s هتبقى P diagonal e power lambda t P inverse P diagonal e power lambda s inverse of P. صح كده؟ فدي هتبقى identity multiply diagonals دول مع بعض هتطلع diagonal. هي سهلة في diagonalization. Again you can prove using the expansion. What about the inverse of e power at? I want to multiply by another matrix here to get the identity. So this matrix would be the inverse of this guy. What to write here to get the identity? E power negative at. If you sum this guy, sum the exponent as this guy says, put s equal negative t, you will get e power 0 matrix, which is the identity. So simply the inverse of this guy, just replace t by negative t. What about power a plus b times t? E power a plus b times t. Let's get back to the expansion. These guys should be I plus a plus b t plus, this is Maclaurin. Is this equivalent to e power at times e power bt? Let's try to expand. The first one, I plus at a square t square over 2 factorial, blah, blah, I plus bt plus b square t square. Are these guys equivalent? You will get I, a plus b times t. You will get I times bt and I times at, so this guy is the same. What about this guy?
في ترم اللي هو 2ab.
Be careful بقى هنا هيطلع لي ايه a times b صح؟ يعني في a square t square وفي b square t square ده مظبوط اهو بس
في ترم ab
الكروس تيرم هيطلع هنا اي بي صح؟ لما بتاع دي لو تفتكر بيطلع ايه؟ a square و a b و b a and b square.
بس لو both matrix are invertible ده ممكن يعني.
لا فالكونديشن ايه عشان دول يبقوا equivalent؟ ان لازم a b تبقى equal b a. لو تبقى الماتريكس الكوميوتيتيف ففي الحالة دي هتلاقي ان الاثنين دول equivalent لبعض. طيب احنا نستدي بس properties للاكسبوننشال اوف ا ماتريكس عشان دي زي ما بقول عاوزها في solution of differential equations. اهم حاجه بقى عندي اللي هو الديفرنشيشن ده اللي اكشلي عاوزه عشان اصولف الديفرنشال ايكويشن. تعال نديفرنشيت اي باور اي تي. ادي اي باور اي تي الاكسبانشن بتاعها. تعال نديفرنشيت اي باور اي تي. So when you differentiate a matrix with respect to scalar, you just differentiate each entry with respect to this scalar. So I want to differentiate, for example, the identity. Differentiate each entry with respect to t, which would be 0, because it's constant. And here you have A times T. A is a constant matrix multiplied by the scalar T. So you simply get the derivative as A. مش كده؟ كل entry multiplied by T. فما differentiate هتطلع هي الماتريكس A. What about the next term? يبقى ايه؟
2 factorial a square t.
A square T. أو next term المفروض A cube
يبقى 3
T cube over 3 factorial. فالديريفاتيف بتاعه ايه؟ 3 A square sorry A cube T square over 3 factorial and so on. Let's simplify this guy. So we'll get A plus A square T plus, simplify these guys, you'll get A cube T square over 2 factorial and so on. If you take A common, you will get I plus AT plus A square T square over 2 factorial and so on, which is simply A times e power AT. So the derivative of e power AT equal to A e to the AT. This is similar to the scalar. When you say derivative of e power 2t, for example, you say 2e to the power 2t. مش كده؟ Let's define a vector y as a function of time equal e power AT times a vector constant y naught. And let's find the derivative of this vector. This is a vector function in time equal e power AT multiplied by constant vector. Let's differentiate here both sides with respect to t. So what is the derivative of these guys? We'll get here derivative of each entry, which is y dash. And here the derivative, this guy is a constant. So keep it constant here in its position and differentiate the exponential, which would be A e power AT. So what do we get actually? Y dash equal A times this guy is y. So we'll get y dash equal AY. So actually this is my system of differential equations that I'm going to solve. I'll give you this differential equation, system of differential equation with initial condition y at time 0 equals certain constant y naught, and ask you to solve this system of differential equation. So what you are going to do is take this matrix here, A, and find the exponential of this matrix, e power AT, and multiply it by the initial condition y naught to get y as a function in time.
y نوت هنا فيكتور برضه.
y naught فيكتور في الانيشال كونديشن بتاعك شويه كونستانتس كده. وانت عايز تعرف الواي از ا فانكشن اوف تايم هتتغير ازاي مع التايم، فانت عارف الانيشال كونديشن للفيكتور ده وعايز تشوف مع التايم هيحصل له ايه. بيزد على الديفرنشال ايكويشن الفيكتور فورم. طيب عندك هنا ماتريكس A، كل اللي هتعمله هتحل الايجن فاليو بروبلم للماتريكس until you verify طبعا انها diagonalizable and then find e power AT multiplied by y naught to get the solution. هنشوف ده in details next lecture ان شاء الله. ما دي هي الواي، this guy. Okay. فانا هشوف actually الديفرنشال ايكويشن دي زي انت مثلا في السكيلرز. في السكيلر انا كنت بعمل ايه؟ كان يبقى عندي مثلا y dash equal to y. مش كان عندك حاجه كده فبتقول ايه السوليوشن بتاعها؟ ومثلا مديك y at time 0 equal y naught. فبتقول لي السوليوشن بتاعها عباره عن y naught e power 2t. مش انت كنت بتعمل كده في السكيلر؟ ولا كنتش بتعمل كده؟ دي الديريفاتيف بتاعها بيبقى the same multiplied by 2 فيطلع y dash equal 2y على طول. فانا actually هشوف الديفرنشال ايكويشن دي واقول لك solve such that ده هيبقى شكل السؤال بتاعك. دي البروبلم اهي. انا عارف الجفرننج ديفرنشال ايكويشن وعارف الانيشال كونديشن. بقول لك solve انت تقول لي السوليوشن هو شكل اكسبوننشال فانكشن عشان هي الديريفاتيف اللي بتبقى ايه مالتيبل من الفانكشن. فده السوليوشن بتاعنا. احنا هنا نفس القصه بس بدل ال2 دي بقت ماتريكس. بقت الماتريكس. كل اللي هعمله هعمل نفس القصه. هجيب الاكسبوننشال بتاعه الماتريكس اللي هنا تايمز تي زي ما انت عملت اي باور 2 تي هنا. ومالتبلاي باي الانيشال كونديشن واي نوت عشان اجيب الفيكتور بتاعي. طب as you know بقى مش كل الماتريسيز diagonalizable. فعايزين ميثود تانية that work for non-diagonalizable matrices. فالميثود هنintroduce بس الميثود النهارده ونشوف next time how to find exponential of a matrix using this method. هي based على theorem by two scientists Cayley and Hamilton. Let's see it in this example, simple example. I want to find the characteristic polynomial and I'll call it f of lambda and then try to find f of a. Let's find first the characteristic polynomial. What is the characteristic polynomial? Determinant of a minus lambda I. So find determinant of a minus lambda I, expand. This polynomial is called the characteristic polynomial. Okay, I'll call it f of lambda. Let's try to find f of a. What is f of a? I'm going to replace lambda by the matrix A in this polynomial. So I write it as a square minus 5a plus 6 i بقى ما ينفعش 6 ساده كده صح؟ وتعالى نحسب بقى الكلام ده. a square و multiply a by itself تطلع الماتريكس دي minus 5a plus 6 times i. لما تحسب بقى دي كده هتلاقيها تطلع equal 0. فهتلاقي ايه بقى؟ هتلاقي ان الماتريكس دي اللامداز بتوعها كام اصلا actually؟ لو جيت تجيب الايجن فاليوز 2 and 3 مش كده؟ هتلاقي ان 2 و 3 satisfy الكاركترستيك ايكويشن والاي كمان itself بتساتسفاي الكاركترستيك ايكويشن. فاللي لاحظوا بقى الكلام ده هم الايه اتنين الشباب دول كايلي اند هامilton ان هم لاحظوا ايه بقى ان every square matrix A satisfy its own characteristic equation. يعني just هات characteristic equation replace اللامدا by A هتلاقيها بتساتسفاي. طبعا هي بروف. انا هديك البروف بس السمبل بتاع 2 by 2 بس هم طبعا يوم بروف جنرال على n by n matrix. To prove it for 2 by 2 هناخد ماتريكس جنرال وتعالى نبروف الكلام ده. هنجيب اول حاجه الكاركترستيك ايكويشن بتاعتنا اللي هي determinant a minus lambda i subtract lambda من الدياجونال expand طلعت لنا كده دي الكاركترستيك ايكويشن. remove بقى اللامدا replace it with a the matrix a and a find a square multiply this matrix by itself and put here a square minus a plus d times a plus this guy multiplied by identity. If you take each entry and sum up, you will find that this guy equal to 0. So this is sample for 2 by 2. You can extend this and find the proof for any n by n matrix. One simple application for this is you can get the inverse of a matrix without doing reduction. How? Let's see, for example, this matrix. If you write the characteristic equation and then replace each lambda by A, from this equation, actually, you can get the inverse of A. Do you have any idea how to get the inverse of A from this equation? Multiply by inverse of A both sides. So what do we get? Something like this. So you can get a relation between the inverse of A and powers of A. So simply all you need to do to get inverse of A is to find A squared, subtract 12A plus 21I, divide by 10, you'll get the inverse of A. Okay? So this is one of the applications of Cayley-Hamilton, is to simply get the inverse of A without any reduction. Next lecture, inshallah, we'll see how to use this to get the powers of the matrix and the exponential of a matrix using this theorem. Any question? So the main point today is how to find the powers of a matrix using diagonalization, how to find the exponential of a matrix, and e power at for diagonalizable matrices, and Cayley-Hamilton, that any matrix satisfies its own characteristic equation, and from this we can get the inverse of a matrix without reduction. Any question? Okay, shukran.